So when we build in the circuit, we know that in order to measure the current and the voltage across the resistor, we have to use the ammeter and voltmeters. However, the instrument you use should not disrupt the measurement itself. So therefore, the resistance of the ammeter should be as small as it could, but the resistance for the voltmeter should be as large as it possible. Now let's go to the chapter 22 for the magnetic field. And you will find out there are many similarities between the electric field and magnetic field. For example, magnet has two poles, north and south. So north do not like the north and south do not like the south, but north and south like each other. And also, the magnetic field lines can be visualized by the magnetic field lines. And the directions of the line follow the convention. They always point away from the north and always point toward to the south. But the only main difference is that these two poles always appear in terms of pair. So you never can find out the isolated north and south pole. And how about the magnetic force? So the magnetic force is a little bit tricky in these chapters. So first, let's study that. When you have a charge moving in the magnetic field, what is the magnetic force? So this is a formula, but this is only true when the electric charge is moving. So it depends on QV. And the right-hand rule is try to help you to determine the direction of magnetic force. And hope you still remember that the first right-hand rule I teach you is that the forefinger is the direction of the charge, the current, the charge, and you should curl your forefinger to the direction of magnetic field, and the thumb will be direction of the force. And if the charged particle is moving parallel to the magnetic field, then there will be no force. So which means the direction of the charge should be perpendicular to the magnetic field. This is a very unique difference in the magnetic field. And if the charge is moving perpendicular to the magnetic field, then they will not be accelerate in the direction of magnetic field. Instead, the force will be also perpendicular to the charge. So therefore, the movement of the charge will be in a circle. So in some special condition, they might move in a helix. And now this is the second case, but very similar to the first one we studied. Instead of one charge moving, it is a wire carrying the current. Okay, it is a long wire current. So they may experience a force also when you try to put them in the magnetic field. And let's assume that the length of the wire is capital L. Then the force is ILB, but the theta is also related to the angle between the direction of the current and direction of magnetic field. But no matter what, the direction of the current and B should be try to perpendicular if they could, based on the sine theta here. If they are parallel again, once again, there is no force. And the right-hand rule can also be used here. And because you have a force, so now consider you have a current loop. So this is a problem. You also see that in the test too. So if you have a current loop in the magnetic field, then there will be a torque. So make sure you know how to get this result. Now, we just studied the electric field in the previous 3 chapters. And we find out, actually, the electric field will produce a current, and the current will create a magnetic field. And the directions of the magnetic field is determined by the second right-hand rule. Now, the thumb is the direction of the current, and the forefinger, when you curl the forefinger, it is the direction of magnetic field. And now, very similar to the Gauss's law, we introduce the Ampere's law, but if the format is completely different. So now you can calculate the magnetic field parallel to the direction of the closed loop you choose. So this is a closed loop, and the magnetic field should be parallel to that. Then now you can calculate this magnetic field flux, or I should not even say the flux, magnetic field along some directions. And they can be calculated in terms of the current enclosed by this closed loop. Remember, this delta L is a closed loop you choose. They definitely have to be closed. So within that closed loop, what are the current will be enclosed by that loop? And for a long wire, straight wire, the magnetic field produced by a long wire current is this format. And now, if you have 2 parallel current wires, then they will exert a force on each other based on what we have studied before. then the magnetic field for the current loop is similar to the distribution of magnetic field produced by the bar magnet. And that's the reason that for the current loop, the current loop, if you try to curl, this is the third right hand rule, you try to curl your 4 fingers, then now the thumb will be the direction of magnetic field. And this is actually what the bar magnet just showed you. So here you should see the difference. Previously it is a long wire current. The second one, it is a current loop. Okay, so the current loop is different. And when you try to apply the right hand rule, and the field produced by the current loop is this formula, and you will say they look similar, yeah, but different. So be careful. And when you try to accumulate more and more current loop, it becomes a solenoid, yeah. So this is a formula for the magnetic field. So before you try to remember that, I would strongly suggest that you should know that how to use the Ampere's law to get that. Ampere's law is the most important concept in the chapter 22. Okay, so now let's go to the chapter 23. So we find out that now if the strength of the magnetic field is not a constant, if it keeps changing, then there will be an induced current produced depending on how fast the magnetic field changed. So now we are going to define a quantity in order to describe this one in terms of formula. We calculate the so-called magnetic flux. So magnetic flux is the magnetic field lines passing through a cross-section area. So the concept is the same as the electric flux, except this is the B field now. So the Faraday's law basically summarizes what you say here is that if your magnetic field is changing, which means the magnetic flux is changing with respect to time, then they will produce an induced EMF. What is the induced EMF? It is a voltage difference. So once you produce an induced EMF, they will produce an induced current. So this is very important in the chapter 23. So very similar to the Faraday's law, but Lenz's law is a very important one to let you understand the physics of that. So why the induced current is produced and what is the direction of the induced current is flowing in that direction is because the most important concept for the Lenz's law is they always try to produce a magnetic field, try to against the change of the magnetic field. So which means if the magnetic field is become smaller and smaller, then based on the Lenz's law, they will produce an induced current, and this induced current will produce an induced magnetic field. They will try to against the change. This induced magnetic field from the induced current will try to against the change. So this is a very crucial point for our concept for the chapter 23. And then for the solenoid as a bunch of coils piled together, then for this kind of particular instrument, we define the so-called inductance. So based on the Faraday's law, we know that if you change the magnetic field, you will produce an induced current. So which means the current force in the coils also will change with respect to time. So now the induced EMF can be related to the difference, the change of the current with respect to time, multiplied by a constant called, or the quantity called the inductance. This inductance is for the coils. Okay. Now I'm going to skip. So this one, then for sure, like the two parallel plates in the electric field, so they also can store the energy within the inductors. So the magnetic field energy density in the inductors can be written in terms of this. And the transformer equation is related to the Lenz's law. So make sure you know that how to get this relation. Now let's move on to the chapter 14. So now we are in the topic of the test 2. So we start to study the concept of the wave. So there are two different kinds of wave, transverse and longitudinal wave. So how do we define these two? It depends on the medians. It's moving perpendicular or parallel to the propagation of the wave. But no matter for what kind of wave, the wave speed is always determined by the multiplication of the lambda, the wavelength, and the frequency. But now let's try to study that the velocity, speed of the wave on the string. So this is a unique case. This is a transverse wave, and this is for the string only. So the speed of the wave on the string is determined by the tension and divided by the mass density. So how did you calculate the mass density? It is the total mass of the string divided by the total length of the string. Then we find out that there will be some interesting effect happen if you try to attach one end of the string and it is fixed. Then the wave reflected, the reflected wave will be inverted. But if the end is free and allowed to move, then the reflected wave is still not the same as the original wave. They will not be inverted. And this is due to the phase change of that. And this is true for the transverse wave. And now the second example for the longitudinal wave is a sun wave. So it is due to the compression of the medium. Yeah. So now let's try to study a little bit more. So we know that the sun wave also have the pitch. So the pitch is related to the intensity of the sound. Now we define this called the unit, the beta, to define that how loud it could be. And then we studied that the very important concept in the wave propagation is the Doppler effect. This is the change of the frequency due to the relative motion between the source and the receiver. So the most general formula is this one. So the O is for the observer and the S is the source. So this is the relative velocity between them. And V is the velocity of the speed of the sound. So when there are two, if you now consider there are two sources produce the wave, when they propagate in the space, they will have an interference. So if the two waves are in the so-called in phase, so the interference will be constructive. All the rest will become destructive. And there is a so-called perfect destructive interference is that they are exactly 90 degrees out of phase. So they will cancel perfectly. So there's an interference patterns produced by this kind of wave properties. So now if you have a standing wave case, so what is a standing wave? Now you produce a wave along a string, but this string two ends are fixed. So they will be reflected by the other end. So they will be considered as always two waves interfere with each other. And they will form a pattern of the wave, which since it is stable there. So this is the concept of standing wave. So the standing wave produced on a string, which is the two end fixed. This is the way how you calculate the frequency and the wavelengths for different kind of wave, standing wave mode. Remember, this is for the two end fixed. So if you have one end open, one end fixed, this is a formula. And I hope you already notice the difference. For both ends open here, n is an integer from 1, 2, 3, 4, 5. And for the one end open, one end fixed, it's 1, 3, 5, 7 only. If you have both ends open, actually the result is the same as the both ends fixed. Now let's go to the chapter 25. So we start to study that actually the electric field and magnetic field are not two isolated objects. They are connected together. So actually when the electric field and B field are oscillating, they will produce the so-called electromagnetic field. So this electromagnetic field will propagate in the space in the direction perpendicular to the electric field and magnetic field, which means EM wave is the transverse wave. And how do you determine the direction for each of them? Once again, it is a right-hand rule. So the right-hand rule is that the forefinger is the direction of the electric field. So you curl your forefinger to the direction of magnetic field, and the direction of the thumb is the direction of the wave propagation. And finally, we have shown you that any accelerated charge can produce an EM wave as a source. As long as you carry the charge and you are changing your velocity, it will produce the EM wave.